This is day one of the nuclear physics notes, and we were going to start off by looking at the atom and answering a couple questions that you should be able to do coming from a chemistry class. Let's take a look. What type of atom is this? In order to determine what type of atom this is, I would look at the number of protons, and I assume the red's the protons here. 1, 2, 3, 4, 5, 6, 7, 8. So I find 8 protons in this nucleus area. And then I look at the periodic table and I'd be able to determine that the only thing that has 8 protons is going to be oxygen. So where do you find the protons? Right there in the nucleus. Where do you find the neutrons? Also in the nucleus. Where do you find the electrons? You're going to find those in the clouds around outside the nucleus. How many protons does it have? I counted earlier, 8 protons. How many neutrons? 1, 2, 3, 4, 5, 6, 7, 8. I found 8 neutrons as well. Is this a neutral atom, and how do I know? Well, in order to know that, I know that the 8 protons each bring in a positive charge. So there's going to be 8 positives. And then I have to count the electrons, each bring in a negative charge. 1, 2, 3, 4, 5, 6, 7, 8. Also 8 negative charges from the electrons, so this would be a net charge of 0, and this would be a neutral atom. Let's start by looking at the basics of an atom. In the nucleus we have protons with a positive charge, neutrons with no charge. These are all called nucleons, just a generic term for anything you find in the nucleus. And outside the nucleus we're going to find the electrons, which have a negative charge. And they almost have no mass relative to the proton and neutron. So the nucleons, they occupy the nucleus. They consist of positive charged protons and neutral neutrons. They're almost 2,000 times the mass of an electron. Now, if I was going to look and try to figure out how to draw an atom and figure out how many protons an atom would have, I would have to look at the periodic table. And the atomic number is going to be very useful to me. The atomic number tells me how many protons this boron is bringing in, or has. All borons have to have that 5 protons. The neutron number could change, and therefore the atomic mass could change, but if it has an atomic number of 5, it's going to have the properties of boron, and it's going to bring in 5 electrons. Of course, those can be shared. Different things can go on with electrons, but we know that this boron has 5 protons based on its atomic number. So we got the atomic number here, 5. We've got the atomic mass here. Now, the atomic mass is really relative to all the borons that you find in nature. So looking at this, I would assume if I'm going to pick a boron out there in nature, I'm more likely to find a boron that would have 6 neutrons, and therefore boron 11. The atomic mass, this number right here, is just a blend of all the different types of isotopes of boron you find in nature, and within those isotopes, the average of those would average to 10.811. So with that being said, I assume that the boron 11, this is closest to 11, would be the most common boron found. So atomic number is the number of protons. Atomic mass is the protons plus the neutrons. Leave out the electrons because the electrons are so small. And then the atomic number also would be the number of electrons that this boron would bring in if it was uncharged. So let's take a look at this question. Here we have aluminum 27. 27 just tells you it's the atomic mass of aluminum. And how many protons would it have? Well, looking at the atomic number, I would say 13 protons right there. How many neutrons? In order to figure out the neutrons, I would have to, I'm going to do it up here, I would have to take the total number of protons plus neutrons, and I would subtract the number of protons from that, and that would leave me with 14 neutrons. When you have a real atom, they only bring in whole neutrons. So you're never going to have a fraction for the atomic mass on a real atom. It's just the atomic mass in the periodic table is averaging all the aluminums if you had a 27 point something. Now, looking at this, how many nucleons there are? Well, those are the protons and neutrons. So here we have 27 nucleons. How many neutrons? Once again, we had 14. How many protons? We had 13. Looking at this, just going with it, just to make sure you're You're here with me. 13 aluminum. 13 is the atomic number, so that's going to be the number of protons. Neutrons, the atomic mass minus the number of protons, leaving you with 15 in this case. And nucleons, that's the 28. Nucleons includes protons and neutrons. Electrons are left out of that number over here. There's 28. No electrons in that number. If I wanted to figure out how many electrons this would bring in, it would be 13. So these are called isotopes, all the different types of versions of aluminum that you can find in nature. Here's carbon-14, the radioactive unstable isotope. And then here's the normal carbon that you would see, carbon-12. 12 standing for the atomic mass, 14 standing for atomic mass. It being carbon, it can only have 6 protons. It can only have an atomic number of 6. Four fundamental forces in nature are the strong nuclear being the strongest, electromagnetic force being the second strongest, weak nuclear force being the third, sometimes mixed in with electromagnetic, and then the fourth being gravity being the weakest fundamental force. In explaining and kind of giving you some reason behind the strength to the weakness, I like to look at the electromagnetic force, and I want you to think about the nucleus. If you had 2 protons, which you find, or 3 or 4, you find these protons in the nucleus, these are all going to want to repel from each other. Now, why does that not occur? There must be a force that's stronger, and that's the strong nuclear force. Under close distances, and there's also going to be neutrons to help this out. We'll talk about radioactive decay later on. But under close distances, the strong nuclear force is going to be stronger than the electromagnetic force, allowing for these protons to stick together. Without the strong nuclear force, this atom, the nucleus of the atom, would just explode because all these positives want to get away from each other. So strong nuclear being the strongest, electromagnetic force is also, it's important for giving all elements properties, all the bonding characteristics that these atoms have in molecules, and everything revolves around the electromagnetic force. The third, weak nuclear force, just know that it's responsible for beta decay. We'll talk about beta decay today. And then lastly, gravity. You can tell that gravity is a very weak force that relates masses and how much they attract each other based on their distance. Because looking at the universal gravity constant, or G, capital G that we use, at 6.67 times 10 to the negative 11th, which is a really small number. Radioactive decay is caused spontaneously when you have unstable atoms. For example, this unstable fluorine will break down and all of a sudden become oxygen as it gives off one of its protons. This occurrence is called transmutation. Now, why do atoms decay? The main reason is because you have either large nuclei. For example, this is a proton number, 82. Well, if you have 82 protons, you come with a whole lot of neutrons, and then that mass, the nucleus, that's the strong forces in that nucleus aren't enough to keep those nuclei together. So over time, depending on what atom you have, you'll have a half-life, some sort of timing where the atom will decay over time, over maybe 100 years, maybe 1,000 years, maybe hundreds of thousands, but they'll decay into something else. Another reason why you have unstable nuclei are just having the wrong neutron to proton ratio. Every time you bring in a proton and a neutron equally, as you get bigger and bigger and bigger, this whole area is all unstable. In order to have stability, you need extra neutrons for every proton you bring in after a certain atomic number. So they'll just spontaneously decay, and this leads you to half-lives, which will be a future lesson. And the reason why decay occurs is so you can have stability. So you have a different element that's going to, or a different atom that's going to be more stable as a result. Marie and Curie, 2 scientists that discovered radioactivity, and they discovered it with polonium and radium. And then when it comes down to particles, the main particles we're going to look at are alpha particles, which come with 4 atomic mass of 4, but really 2 protons, and 2 protons would be a helium atom. So this is the common symbol 42He, or just that little alpha right there. Beta decay, symbol beta right there. And if you're writing an equation, you will often write 0, -1, and then E to stand for electron, because it's nothing more than just an electron. And in gamma, it's nothing more than energy given off as orbital electron changes in orbital. So it's energy only. And when you think about the particles, alpha is the biggest, beta is smaller, and gamma is energy only. So they can get through different sheets of paper. There's kind of a gauge of their penetrating power, whether they can get through paper. Alpha particles are just too big, they get stopped by paper in most cases. Beta particles, which are electrons, they can get through paper, but they get stopped by aluminum. And then you get to gamma, and that's part of the reason why if you have high radiation, you will wear something that's lead-based, because they can usually not get through lead, or at least for most cases, they're going to get stopped by lead. Now, looking at alpha decay, so here's an example. You start off with a uranium, and then that's going to decay. And when that decays, it gives off this alpha particle, that 42He, and then in a balanced equation, these two on this side, anything on the right side has to equal the left side. So I count the top numbers, 234 plus 4, and I get 238, 90 plus 2, and I get 92. And so here's an example of uranium decaying into thorium with an alpha particle released. Beta decay, here you'd have thorium going through beta decay, and it's an electron given off, and what's weird is that the electron comes from a neutron, and it leaves a proton as a result. So the mass doesn't change because the electron's given off, and that doesn't really have much mass. It doesn't really go into the atomic mass, it's just too small. And so the electron's given off, and when it's given off, the atomic mass stays the same, but the proton number goes up because one of those neutrons, which was in this 234 before, is now a proton, and so it's adding to this number. When looking at this reaction right here, and same thing as before, everything on the left of the arrow should equal everything on the right. So the decay reaction, 234 plus 0 equals 234. 91 plus minus 1. So this is important. You're losing an electron and gaining a proton in the result as a result. So 91 minus 1 is 90, and so this is a balanced reaction. Gamma, it just goes into there's energy release, but what you had before equals what you had before have after. It's the same element afterwards. So let's just take a look at how we would do one of these. Now here's an alpha decay question. You have it in your notes, 3A. And so you have 214, the atomic mass of 214 polonium. And this also, just to kind of get you prepared for some of the other notes you'll have later on, this would be labeled PO, or polonium 214. Polonium is always going to come in with 84 protons, but it's going to have different numbers of neutrons, leaving you with a different atomic mass as a result. So polonium 214 just means that this is a specific isotope that has 214 minus 84, whatever that ends up being, 130 neutrons. It's a specific isotope that has 130 neutrons. So you have this polonium, helium is given off because it's alpha decay, and then you ask yourself, okay, 214 minus 4, that ends up being 200, and then 84 minus 2, that's 82. So here 82 plus 2 ends up being 84. These are balanced, and then you look off your periodic table. When you look off your periodic table, you find what is the atom, what is the element that has an atomic number of 82 protons. And looking at that, that's going to be lead. So that's how you do this example. Now here's a beta decay example, same sort of process. 209 plus 0 equals 209, so that's correct. And then what plus negative 1 equals 82? Well, 83. So that number 82, you're going to become something more. You're going to gain a proton because it came from that neutron. And so 83 on the periodic table, when you look at the periodic table, it ends up being Bi, or bismuth. So here would be the reaction for 3B. And this is just showing you more of what happens, what really truly happened. The atomic mass didn't change. You gain a proton where there was a neutron. And then this beta particle here would be your beta particle. This beta particle, the 0, negative 1e electron is given off. Here's an extra question just to kind of get practice. If you ever see it this way, what you'd have to do is go ahead and let's say, what is a beta particle? Well, that's an electron, 0, negative 1, and then you can balance it. So here it would be, this would be carbon-14 decaying, 14, 7, and you look off your periodic table, and that ends up being, you've got yourself nitrogen. Going on this one here, this would be alpha decay, and alpha decay would be 42He. This is more useful when you're doing an equation. So subtract 4 from 238, you get 234. Subtract 2 from 92, you get 90. Look off the periodic table, what's 90? Atomic number of 90 would be thorium, Th. And so that's how you would do this.